Start recording and start the screen share with an update on course evaluations. So can you see where we're at as a group? This group is currently beating my other class. So 5 out of 9 have completed evaluations out of 14 out of 29 for the others. And you can see previous semesters in here too. Last fall hit 100% in both courses. Let's see if we can beat that. Some people still need to get it together. Well, good news is that you have, I think, another week and a half roughly to do this. So, and you can see my first semester here, why I originally started doing this. I had a response rate of 40% my first semester here, 2 out of 5 people. So it's pretty hard to take a mean across 2 people and have that be a meaningful concept. So since then it's gotten a little bit better. But anywho, thought I would give you the update on that. Let's see, hide that thing. Any homework 6 questions that I can answer so far? Not yet? That's fine. I'm just asking. It's my duty to ask. It's not due for quite a while, but I will say in terms of the sections, the first section is just a main effects model, which is something that you could easily do now, and hopefully by the end of today you would be able to do section 2 as well. So just we're closing in on the end of things here. Anything you want to talk about before we jump back into where we were last time, interaction terms and such? No? We're good? All right. I just thought I'd ask. Then where we want to start today is example 6. So we did all of the slides last time going through the logic of how one takes an interaction term and describes what it's doing to its constituent main effects. And so now we get to put that into practice. So I've got example 6 here. This example corresponds in part with chapter 2 of my book, which is on your reading list right now. So the textbook that I wrote is all about longitudinal analysis. But I had found in teaching those models that so few people had been trained in how to interpret interaction terms just in regular single level models that I had to do that as a unit in those courses. And so that's why chapter 2 of the book is covering just regular old regression and how to think about main effects and interaction terms in those models. And so that's where this is coming from. So if there's anything that's in here that it goes too fast or you want to hear it again, in addition to rewatching the videos, you can read the chapter, because a lot of this will correspond exactly to how I would describe it in there. So the story behind these data, these are fake data based on real data. So there is a longitudinal study that I was involved with in terms of the data analysis when I was a postdoc called the octogenarian twin study of aging. So it was a study of same-sex twins who were recruited at the beginning of the study to range between 80 and 100 years old. So a very unusual sample. And they were measured for up to 8 years, up to 5 occasions. So that data was the genesis at the baseline occasion for these fake data. So I used basically real parameters from the data to simulate fake data, much like I do to build your homework data. And the variables involved, we're going to be predicting an outcome that is called cognition. It's based on the information test, which was a measure of crystallized intelligence. So it's something that you would not expect to change over time unless there was some kind of dementia or other kind of specific health-related decline. We're going to be predicting it from chronological age, because when you do cognitive aging research, you must control for age at all times or someone's going to yell at you. Age is going to be centered at 85 years because that was near the mean of the sample. And we also have grip strength, which you may be thinking, what? Like, what? But it is a measure that is often used as a proxy for physical functioning and frailty in older adults. And so you have to squeeze something and it measures how many pounds per square inch that you can squeeze. So it's centered at 9 pounds per square inch because that was near the mean of that variable. We have a binary measure of gender. So we have that as men versus women is the way that it's going to be coded. And then a categorical predictor as to their status with respect to dementia. So in the original study, there were people who never were diagnosed with dementia, either prior to the study, during the study, or afterwards. And so that's the none group, and that's the most prevalent in this case. There was a group that, after baseline, at some point during subsequent data collection, they were diagnosed with dementia, and so that is the future group. And there were actually some participants who already had dementia, but they were still able to participate in the study at least once, and so that's the current group. So dementia, of course, is bad for you. It does bad things to your cognition and other physical and mental abilities, so we would expect that to have a negative effect. So the first set of models here is going to just look at the main effects of each of these predictors in predicting cognition, and then the next 2 or 3 sets of models, I can't remember how many I've gotten here, I think it's just 2, are going to add interaction terms. So in terms of the data input and data manipulation, so this is going to look a little bit different than what you're used to, because this example uses an actual SAS data set and I think an actual Stata data set as opposed to bringing it in from Excel. So the same file save reference is used to define the path to the folder where the data reside. However, there's also a SAS-specific line that I've added here, which is called a libname statement, which functionally does the same thing, but it only applies to SAS datasets. So the first thing here is defining a more general abbreviation that I can use anywhere in the code. SAS datasets, output files, anything I want. The second one then references that in defining this SAS-specific library. So I've called it the same name because it's the same place, but this file save on this line corresponds to this file save right here. So what I'm doing is defining a library, a place where SAS datasets reside, and then it knows to look inside that location and to find a data set that is called SAS_chapter 2. Since it's from chapter 2 of the book, that's what it's called. So it's going to read this line first and come up with the path name. It's going to substitute in that path name to define what file save means with respect to the SAS data set, and then it's going to go find this file, make a copy of it, and save it in the work temporary directory as example 6. So I'm importing a real SAS data set directly into SAS and saving a copy of it in the work directory. And do you remember why I do that? We may have talked about this a long time ago. The reason is that in SAS, all transformations to a dataset happen immediately. If you screw up, it's gone. And yes, I have overwritten files on my hard drive before because SAS lets you do that. So to protect myself from my own whatever, I immediately bring the copy, make a dataset copy and put it in the temporary directory. And then all of the changes that I make apply to the copy. I don't need to save the copy because as long as I have the code, I just have to run it again and I can get back to the same place. So a general strategy that I use is not to save intermediate data sets unless I absolutely have to, just to have an original and then work with the copy when I'm doing it in practice. So this is the data set that's being worked on now in the work library called example 6. Okay, does that make sense? The copy part? Yeah. So like when I used to use SPSS once upon a time, that was the first program that I learned. And I'm so old, by the way, that SPSS didn't even have a GUI when I learned it. It was code. And then it became like the Windows version that everybody knows of as SPSS. But in SPSS, if you do something to a data set and you realize you've screwed it up, you can always exit out of the data set without saving and you have the original back. You don't have that privilege in SAS. So it's a workaround to make a copy and work with that. So step 1 here, I'm going to center my quantitative predictors. So you will get a chance to practice this yet again in homework 6. And my naming convention is to take the centering constant and stick it at the end of the new variable name. So age 85 is the new column that contains the original age column minus 85. So 85 is going to be my reference UR here for the intercept for these models. Likewise, group 9 is being created from the original group column, subtracting 9. Then we have dummy coding the dementia groups. So I'm first creating 2 empty variables, and the names of these, DemNF and DemNC, to me what that means is it's Dem is the stem for dementia, and then none versus future is NF, and NC is none versus current. So this is another example of using a name that when you're staring at your output will help you remember what it means, as opposed to just like group 1 versus group 2, and then you're like, wait, what was group 1 again? So if you can, help yourself out by eliminating those kinds of working memory issues. So we have, if it's the first group, which is the none group, as I have noted in the comments, then I am setting both of the new predictor variables to 0. So right there, what does that tell me? Gestures?
Yeah, sorry. Is it that that's the reference?
Ding, ding, ding. Yep, and that's going to be my reference group, because the intercept by definition is the expected outcome when your predictors are 0. So I'm setting it up so that the intercept of the model is going to refer to somebody who belongs to the none group, somebody who belongs to the none group who is 85 and who has a grip strength of 9 pounds. That's my reference individual. Then if dem group equals 2, the first predictor variable switches on, so that then that predictor is going to tell me how the future group differs from the none group as the reference. And then if group equals 3, the second predictor switches on to tell me how the current group differs from the none group. Not to be confused with the none group. Ba-doom. We may have had nuns and priests in the study, but I am not privy to those variables. So. And these data were collected, I think, in the 80s or something too. So these people are sort of long past. But and then because I am a good data manager, I add labels so that somebody who's staring at my code doesn't have to try and figure out what all of this means. And these are not strictly necessary, but it's a good practice to get into, to make sure that you attach this kind of information with your variables so that people can know what they mean. And then last but not least, I am making sure that the cases have all of the variables that I'm eventually going to look at. So this, if the number missing across all of these columns is greater than 0, then remove them, delete them from the data set. And the reason that I do that is that the model will do it for you if you don't do it ahead of time. If you want your sample to stay constant across analyses, you have to make sure that your data are complete with respect to all the variables that are in the analyses. And if you want to learn a better way to address missing data than kicking cases out, do you know what I'm going to say?
Take your other class.
Take my other classes, yeah. Yeah, that's the answer. We'll talk about the use of something called a full information maximum likelihood, which is a better way than kicking cases out. But this is what we know how to do for today, so this is what I have here. So any questions on the SAS code to set up these predictor variables? Let me ask you a question then. Do I need to center the outcome of cognition? Is that a
go
thing?
with no.
Yeah, have you ever done that up to this point?
No.
No, it's not a thing. One could, because you end up with an intercept that gets tested against a null hypothesis of 0. And so if you wanted to somehow say that your reference person was different or similar to a particular value, you could use centering to hack that. But no, in general, we never have to center outcomes. We just leave them in their original scale. The reason that we center predictors is so that each has a meaningful 0 value. That's going to ensure that the fixed intercept is meaningful, but more importantly, when we put in interaction terms, it ensures that the main effect slopes are meaningful because they become conditional on the 0 value. So 0 is a big deal. Stata code. Yes, I did do a stata data set. So that's what I thought I had. So in Stata, I am using the same file save convention to create an abbreviation that I can use anywhere in the code. And because I'm importing a Stata data set directly, it is, rather than import, it's the command use. And then I have the path right here for file save, and then stata underscore chapter2.dta. DTA is a stata extension. In SAS, when I created this original stata dataset, it automatically converted all of my variables to lowercase. And so that's why the code is going to look a little bit different, because those variables, because stata is case sensitive, so they all have to match. So then the same thing here in process, I am generating a set of centered quantitative predictors for age and grip strength. I'm also generating an interaction term in order to get semi-partial eta squares. So that is only necessary in Stata because of the way that it does things. Then we have the coding of the dementia groups. So first creating my 2 empty columns, and then selectively changing those empty column values to 0 if it's group 1, 1 and 0 if it's group 2, and then 0 and 1 if it's group 3, labeling all the variables, and then doing the same drop any cases that have missing data down here. Okay, so stare at that for a moment. Tell me if you have any questions. This is all stuff that you know how to do, but just reviewing it. It's never a bad thing to remind you what you've learned. So.
I mean, I'm always able to follow along when we go through these examples, but then when I have to do it myself, I never get it right on my own, and that's frustrating.
You mean you never get it right on the first try on your own, but you do eventually get it right, which is what matters. Right?
Well, yes, but is that okay at this point in the class?
Yes.
Or should I be able to do it like correctly, confidently?
Think of it this way. We all jump into this class at a different point on a learning curve, right? Have you ever interacted with any kind of software before where you had to write code or type syntax? No. Okay, so you're at the bottom of the curve then. You've never done this before. So that it makes perfect sense that it's not something that you are fluent in yet because you just started doing this. Other people who've learned programming languages or who have seen syntax in various forms, this is a more familiar process, and maybe it goes down easier because they're just further up on the curve. But don't beat yourself up over it. Honestly, if I thought that the process of translating this to something that you could use was so easy that you didn't need to practice it, I'd have you do homework a different way. But I have found in practice that, yeah, there is a leap that you have to take to be able to figure out what to change to make it work for you. And I don't care how long it takes you. Just get there eventually, right? And your classmates are feeling the same, right? It's all about where you are on the learning curve. The same is true in your learning anything. Like if you want to train for a marathon, right? Have you run before? It's like, can you run a 5K? Can you run a 10K? Like the marathon training starts at a different place based on your current level of fitness. And if you used to be able to run marathons, but you haven't run for a while, it's probably going to be easier to step into the training than someone who's never run at all. So it's okay. It's perfectly okay. So more practice makes it easier, though. That's what I can tell you. Just like anything else in life, more practice makes it easier. So first model then we have here is what I'm going to call a main effects only model. So you would have known this as a general linear model before. It's a general linear model that has multiple predictor variables in it at the same time. So what that means conceptually is that each of these slopes is a unique effect of that predictor controlling for all of the other predictors in the model. So each slope is going to tell you what that predictor specifically brings to the table that the other ones don't. And I call it a main effects model. Can you guess why? Main effects only model, rather.
You don't have any interaction terms?
That's it. Yeah, I don't have any interaction terms. So what that means is also that each of these slopes, in addition to being a unique effect, is the unique effect for everybody. Unconditionally, marginally. Those are words that mean beta 1 is the effect of age, period. Doesn't depend on your dementia status, doesn't depend on your grip strength, doesn't depend on your gender. So main effects only, marginal effects only. The effect applies to everybody. So the term marginal and unconditional go together to describe this, as opposed to simple or conditional, which is what they become in the presence of interaction terms. Cough, cough, homework questions. All right, so then we get the model. So age, grip, and gender are variables whose effects are described by one slope each. The effect of dementia requires two slopes. So one of the things that I'm going to want to do is to lump them back together to get an overall test of how much dementia group matters, as well as to get the missing contrast for differences between groups. All of this stuff, we talked about this a few classes ago now it's been. I am asking for predicted values to illustrate the results of the model as a function of age and grip strength, holding gender and dementia group constant at 0. So do you remember there were 3 ways that you can generate predicted outcomes to make like a plot with or something like that? One is Excel, which is pedagogically useful but painful and error prone. Number 2 is this, to write syntax. So each of these lines is going to generate what the predicted cognition would be for a person with these particular predictor values. So this exactly follows this equation right here. When you're asking for predicted outcomes, you need to include every single fixed effect that's in the model, because all of those fixed effects work together to generate a predicted outcome. So when I type the word intercept here, for instance, what am I actually referring to? What does the word intercept correspond to with respect to my equation here?
The beta naught, the beta 0.
Yes, beta 0. You can say beta naught. That's not my thing, but people do say it that way. Beta 0. So it's what beta 0 is going to become. That's what the word intercept refers to. And I only need one of them. So at a minimum, predicted values need a fixed intercept. Then likewise, when I type age 85 here, what am I referring to with respect to the equation?
Beta 1,
Ding, ding, ding. And grip 9?
beta 2,
Yep. And this is beta 3, and this is beta 4, and this is beta 5. The numbers then. What do the numbers refer to?
well, that one is a different age. That one's like 90, I guess we would say. But
It'd be
Wait.
80 because there's a negative sign
All
there.
right,
You can
80,
see that,
yeah.
Yeah, yeah, that number corresponds with that parenthesis. So what is the value of the predictor for which you are generating an outcome? I would like to know predicted cognition for an 80-year-old. Okay, so for age, I plug in -5 to get to an 80-year-old because age is centered at 85. Likewise, for what level of grip strength am I asking for a predicted outcome?
6.
6. And yes, feel free also to read the answer from the screen. Because this is my trail of breadcrumbs, right? To remind myself what I'm doing in each of these lines. So I picked plus or minus 3 for grip strength because 3 was roughly the standard deviation. That's a very common way to generate what a low versus a high value would be. I picked plus or minus 5 for the same reason for age. So I'm showing combinations of like low, medium, and high with respect to age and with respect to grip strength. And the values are always conditional on the scale of the variables. and I am deliberately holding these other predictors constant at 0, which means that my predicted outcome is going to be to correspond to a man who does not have dementia, because that's what it means to be a 0 in these coded variables here. So then I have 9 of them, and those 9 estimates are being saved to a SAS data set that I'm then going to do operations on to make a plot with. Okay, so any questions on the code there?
So for the parameters of age and grip, so are these the one that you just set like arbitrarily, or like are these the one that you wanted to find out and that's why you put like age 80, 85, age 90?
Yeah, so typically speaking, you'd want to illustrate what your model says about people who are low on a variable or high on a variable. And the way that that is often defined in absence of particular values that are of interest is plus or minus 1 standard deviation. And so that's what these values are approximate to. If you have a variable that has meaningful values, like years of education, for instance, you might pick 12 years, 16 years, regardless of what the standard deviation is. But it's always dependent on the scale of the variable and what it means. But just low, medium, and high as prototypes, so to speak, is where those came from. Okay. So let me go to, skip ahead for a minute here and get to the Stata code that goes with it. Because those of you who've learned Stata are going to love this part. That line right there, that's 9 lines of SAS code. I wish SAS had this. I know, right? So people like Brian and other people who have pledged allegiance to Stata, this is probably one of the reasons, is because they have a lot of really slick stuff for doing what's called post-estimation, is what it's called in the Stata manuals, but it basically means using your model to do stuff, broadly construed. So in Stata, the first word you type after regress is the outcome. So order matters here with respect to that. After that, I have my sets of predictors here, and I have C dot in front of them because I've found that if you use them in lincom statements, it insists that there's a C dot, and I haven't really learned the rules as to when you have to have it and when you don't, and so to be on the safe side, I just C dot everything. So if it's a continuous predictor, that's what it means. It's being treated as a quantitative variable, as opposed to I dot instead of C dot, which is a different thing. That corresponds to it being treated as a factor variable, which is something I've deliberately hidden from you this semester. Because I want you to know what it's doing for you when you invoke that option. So the manual dummy coding reinforces that process. So then margins is a command that does a whole lot of things. In this instance, it is generating predicted outcomes. So the at section here then tells it what values for the predictors to either hold constant. So when I say C dot, these things equal 0, that holds them constant at 0 across all of the predicted values that are being created. Whereas here, it's giving ranges. So the way to read this is the first number is where the range starts. The middle number is in increments of that. And the last number is where the range ends. Enges. I'm not even sure what 2 words that was supposed to be. Where the range enges. So it starts at -5 in increments of 5 up to 5. So that gets me the combination of -5, 0, and 5. That would have taken, 3 lines of SAS code to get each of those. I do the same thing for grip strength. It goes to -3 in increments of 3 up to 3, and it crosses them. So I get all 9 possible combinations across these ranges with just this one line of code. And it knows that the most common reason why you would ask for predicted values is to get a picture. So we have margins plot as the next command, where I tell it what dimension of the model I want to put as the x-axis, and I can create a name for it and save it as a permanent separate file that gets saved externally to your hard drive if you wish. So the picture that it made, I think I have in here. Yeah, it's right here. So this is the picture that it made for us. And if you want to customize the labels or the axes, I don't know how to do that in code, although I suspect it's possible. But I do know that if you double click on the window, it pops up and you can do things manually in a Windows interface to change the labels and the values and stuff like that. Okay. So pretty slick. Okay, any questions on the state of code? And vsquish, by the way, is just an option that removes blank lines between your tables of predicted values. So it takes up less space in the output. So let's go through the state of output then, since it's nice and compact here. These boxes. So this thing right here, 88. What's that?
Our mean square error or residual.
Yes, it is. Mean square residual or mean square error, take your pick. Conceptually, what is it?
Error not accounted for within the model.
Yep. It is the variability across people in the E residuals. So how much information is left in this outcome that is not captured by all of the predictors that I've included? Is 88 good? Is that a lot? Yeah, is the correct answer. How do I contextualize? I can't talk today. What is wrong with me? I went running this morning and apparently I spent all of my energy. Exercise is supposed to give you energy, but it took mine away. How do you contextualize that 88? Dementia. Hey, I'm not that old. I'm Gen X. I'm not a boomer, damn it. I'm a young Gen X too. How do I contextualize that 88?
Is it with the R squared?
Ding. So that tells me the same idea, but from the opposite perspective. So R squared tells you what proportion of the variability in the outcome has been captured by the model. So we've captured about 28% of the variability in cognition. That means there is about 72% left over. Does that sound right? So that's what 88 means. It's 72% left. And if we want to correct for sample size, then the R square is a tiny bit smaller. Is that good? Is 27% of the variance good? Yes. We got some more. Fayaz nodded emphatically. Why do you say it's good?
The F critical value and the probability, the p value is like 0.
Yeah.
So it's significant. Yeah.
Yeah, 0 to 4 decimal places. Not ever exactly 0. So it's not written correctly from that perspective, but it's 0 to 4 decimal places. And so yeah, the F is 41. F is a per slope test. So it's lumping all the slopes together and then looking at the average contribution of each slope. And 41 is definitely significant. So we would say this R square is different than 0. And both of these things are important. Keep in mind that your significance is tied to your sample size. So in a large enough sample, you could have an R square of like 2% be significant. So I say 28% is pretty good. You could also say it's significantly greater than 0. All right. And this number right here is the square root of that, by the way. So it's giving you the same information, just in a different metric.
But why do we need the root of the MSE?
You don't. If there's a reason, I don't know what it is. I always, in talking about information captured by the model, it's almost always given in a squared form for funsies. Yeah. I could ask you that as like a trick homework question. Like, give me the unsquared version of residual variance and be like, meh. But no, no one wants that kind of funsies. So I've got the coefficients for you here. So coefficient is a synonym for estimate. So these are the fixed effect estimates. The interceptance data is labeled constant and it's last, much to my chagrin. So this is me being nice out here, tying the beta zeros to each of these things here. So 29 tells us what?
The fixed intercept?
Yes, it is. So 29 is the fixed intercept. That tells us
The value of cognition when the grip and age is 0.
Mm-hmm.
Yeah.
Yeah,
Oh, no, not 0. Centered in
yeah, the
80.
centered zero.
Yeah.
Mm-hmm. Yep. So I would say that is the predicted outcome or expected outcome, something along those lines, because it's not exact, but it's a prediction from a model. And it is when all of the predictors are 0. That's what a fixed intercept is. So for an 85-year-old who can squeeze the thing 9 pounds worth, who is, remember how this was coded?
A male without dementia.
Yeah, so I always put the reference of the contrast first. So MW to me means men are the 0 and women are the 1. And without dementia, the none group. And then the versus the future, none versus current. So 29 is my you are here sign. From there, I can talk about what happens to that hypothetical person as a function of moving up or down along each of these variable lines. So if we start with age, what does that tell me? The slope for age is a negative 0.4. Yeah, I'll take gestures on this one. Slope
It has a negative relationship with it. So I guess
Mm-hmm.
the younger you are, the more grip strength or
Cognition's the outcome.
Oh, yeah. So the younger you are, the better cognitive ability you have.
Yeah. Yeah, or the older you are, the worse you do on this test. And how much worse? Well, so the slope is always the effect on y for a 1 unit difference in x. So if we put the units onto this, it's per year of age. So for every year older you are predicted to score lower on this cognition test by 0.4. 0.4 per year lower. Is that a lot? Well, you have to know the scale of the test to answer that question. I don't remember the scale off the top of my head, but I can tell. But is it significant? Yeah, I got to go drive over here to my p-value to answer that question. So it is unlikely to observe a slope this strong if the null hypothesis of 0 slope were true. It would happen less than 0.001% of the time. How about grip? Everyone want to put the sentence? It's 0.6. Yes, I'll take.
So the harder you can squeeze, the more cognition you have.
Yeah, the stronger you are, the smarter you are. So make sure you hit the gym so that you can continue to develop your mind. Yeah, there's no causality here, but yeah. In older adults, there's a saying that it all go together when it goes. So people who are more physically capable still, I guess, are more mentally capable still would be the way I would think about this. But so for every additional pound you can squeeze, cognition is predicted to go up 0.6. And that one's also significant. Gender. Men versus women. How do I talk about that negative coefficient of 3.66?
If you are a man, your cognition is bad.
If you're a man, your cognition's bad? Or is if you're a woman, your cognition's bad?
I missed the which one is which, but I had a 50-50 shot there.
You did, but yeah, we're on the right track. So I don't know if you can see it when I highlight it, but this is negative. It is coded 0 are the men and women are the 1.
Other way around then, yeah.
Other way around. So yeah, this is another where the wording relative to men as the reference, this slope is telling us that women are lower by 3.65. So direction matters in the dummy codes with respect to who is higher, and that's significant as well. And then people who are going to be diagnosed are 5 points lower than people who will never be diagnosed. People who already have it are 16 points lower than people who are never going to have it. And what about future versus current? Do I know if they're different yet? Could I know that? Yes, Alex. What would you do, Alex, to find out if they're different?
Put in DEM, future versus current, so it'd be FC, not CF.
You could
Right.
recode the variables to make one of those the reference, and so that you would get that information. That is what I originally learned how to do, by the way, back in dinosaur SPSS land. But there's a way that doesn't require rerunning the model.
Could you do the future F test or whatnot?
A future F test or whatnot. Yes.
I don't remember what it's called. I just remember that we've done it in the last homework.
Yeah, you've done it in several of them by now, I think. You can do, it's called Lincom in Stata to get the model implied mean difference. And it would be this slope right here minus that slope is what the code would be. It's called estimate in SAS. So yep, either way. And then these are the predicted means, and there's the graph for that. So each of these slopes is a main effect that is marginal, that is unconditional, that applies equally to everybody across the sample. That will change once we start adding in interaction terms. Okay. Going back to the SAS code for a minute, exact same stuff. We are, right, I had to write extra code to make a plot, but I did that and it's here. So the code's available to you online. That's not something I'm going to ask you to do in homework to make pictures, just something I want you to know how to do in life. All right. So you ready for your first interaction model? Maybe. So I knew at this point in the semester that subtlety is a bad idea. So note the heading for this page on page 4. For homework 6, look at this one. Use this one as your starting point. So I have added 2 interaction terms. I'm looking at whether or not my binary gender predictor interacts with age and whether it interacts with grip strength. So conceptually what I'm asking, one way to think about it is, do men and women have the same effective age in predicting cognition? And do men and women have the same effective grip strength in predicting cognition? Am I frozen? No? Okay, good. Just checking. The other way to think about it is, are gender differences the same across age and grip strength? So we can think about it from either way. So first the SAS code and then the Stata code. My 2 new interaction terms are, I put them on the second line here. So SAS doesn't care whether you return your line or keep typing infinitely to the right side. So I just return it so that it fits on the handout. I have the star here defining each of the interaction terms on the fly. I'm still asking for the same output otherwise, although I've added a few things. So first off, there's an estimate statement to get the missing dementia group difference. So we have the slope for none versus current as the 1, And then the slope for none versus future is the -1, and that gets us the beta 5 minus beta 4 gets us that missing difference. I'm also adding in, I believe this is the F-test thing that you were referring to, Jerome, just a minute ago. The contrast statement. Contrast is a way to lump together multiple slopes to get a joint test of their significance, and it's useful in several different contexts. The one that it's being used for here is to get an overall test of whether dementia group matters. Because there's 3 groups, which means there's 3 possible means, which means there's 3 possible mean differences. And so I want a joint test as to whether there are mean differences across those 3 dementia groups. So I'm asking for that in addition to the specific comparison between the 2 non-reference groups that I was lacking before. And then last but not least, cough, cough, homework question. A joint test of the 2 new interaction terms that I added to the model. So this is the exact same concept that you did in homework 5 when you added 2 new slopes and I asked you to test the contribution to the 2 new slopes. It's just that these are interaction slopes. So the comma is one thing that's easy to overlook, but it's important. The comma is used to delineate numerator degrees of freedom, so that SAS understands that what I want is a joint test of whether each slope is different than 0. If I deleted it, it would run, but it would not give me the right answer. Without the comma, it would literally add the 2 slopes together and then test that one new combined slope against 0. So it's a different thing. So we'll keep the comma in there. Okay. With me so far? All right, then I'm going to then demonstrate how I would ask for what the age slope is for men and women and what the grip strength slope is for men and women as an additional piece of information that I would want to know about this model. So if I'm focusing on the age slope, the rules are start with the overall model, find all the places in it that have age, and pull them down. By the way, if you're not somebody who tends to write out equations for all of the models that you estimate, you can always cheat by just looking at it right here. That line of syntax is a pretty good representation of your model. So I want to have all of the terms that contain age in them, but only those terms that contain age. That's how I'm going to ask for what the age slope would be as a function of any interacting variable. So within that list, there's only 2. I have beta 1, which is the effective age, and I have beta 6, which is how age interacts with gender. So after we identify all of the terms that have the slope that you're trying to get an estimate for, then you factor out the common part, that's age, and it goes behind, and the term that's in brackets right here is the linear combination that gives you the ingredients for how the model tells you what the age slope would be for any person. So then those 2 contributions are all that are required to write an estimate statement. So if I want to know what the age slope is for men, age 1 refers to this beta 1. So at a minimum, I need 1 beta 1. And then the interaction term, why is this 0 right here? What does that 0 correspond to?
To men, because they're the not control, but the one that we're looking for.
Yeah,
Yeah.
They are the that's the value that goes with this variable right here. Yep, I understood you. Yeah, men are coded 0. That's why if I want this for men, this goes to 0. So I didn't actually have to write this line. Yes, you're not on your treadmill today, so you got to get the workout in. I didn't actually have to write this line because the age slope for men is what beta 1 means. I did have to write this line though. The age slope for women, I plug in a 1 for the gender variable which goes here. So now I know I will get output for all three things I might want to know about the age slope. Whether it's significant for men, whether it's significant for women, and then whether those are different. Likewise, if I want the simple grip slope, typo, then I go to the model, find all of the terms that have grip, here they are, and then factor out grip as the common variable, and now I have the ingredients for how I would get that slope. So then, why is this a 1 right here?
That's how many times it's in the equation. Sorry.
Oh, I was gonna say you need the beta 2
Yep.
still.
I need 1 beta 2, that's why. Exactly. And this is a 0 because it's for men, which goes with this variable. And this is a 1 here because it's for women, which is what goes with this variable here. So generally speaking, when you're writing out these kinds of statements, the thing you're trying to estimate always gets a 1. So if I'm estimating a slope, the name of that slope, I need a 1. I'm trying to get the grip strength slope. That's the whole point. It gets a 1. Up above, I was trying to get the age slope. It gets a 1. If I'm trying to estimate a predicted outcome, that's an intercept. It's a conditional intercept, and so the intercept would get a 1. So the thing you're estimating always comes first with a 1, and then the question is, what moderates that? So in this model, there's only one term that moderates the effect of age, and only one term that moderates the effect of grip strength. So then generating predicted outcomes requires having those new interaction terms as part of these statements. So in your homework, you'll get a chance to practice this as well. The most common error that I've seen is forgetting these interaction terms in here. So I am generating the same set of predicted outcomes as in the previous model for low, medium, and high of age crossed with low, medium, and high of grip, holding gender constant and holding dementia group constant. So the thing I'm trying to estimate is a predicted outcome. That's what the intercept tells me, so it gets a 1. I am estimating it for a man, so gender gets a 0. I am estimating it for an 80-year-old man, so age gets a -5, and I'm estimating it for an 80-year-old man who can only squeeze 6 pounds. Okay, yeah, I'm looking at my math here, making sure that it's right. Why is this a 0 right here for the interaction term? Any ideas?
Is it because male is 0?
Ding, ding, ding. It's because 0 times -5 is 0. The interaction terms are literally the multiplicative combination of whatever you put over here for the variables the first time. So all of the predicted values that involve men, their interaction terms are going to 0 out because men are the reference for the model. The main effects cover what happens for men. To figure out what happens for women, the interaction terms kick in. And so this is a -5 here because I had said 1 for women times -5 for age, and 1 times -5 is -5. Okay, how are we doing? Okay enough? Stata code looks very similar with the exception of the hashtag or pound sign. Since I'm Gen X, I'm going to go pound sign. Pound sign for the interaction term. The lincom statement gives you a single degree of freedom, new linear combination of your fixed effects. That's the analog to estimate. So I'm asking for the remaining group difference between future and current. Test is the new f-test thing. That's the analog to contrast that lumps the two dementia group contrasts together to give me an overall test of whether group matters. And then the second test statement lumps together the two new interaction terms so that I can talk about how they contribute relative to the previous model that did not have them in there. So I'm lumping these things together in different ways to tell me different things. And then lincom statements are analogous in terms of the interactions, except that you have the multiplication by the values entered as explicit here, as well as the fact that they're being added together as explicit as well. So the simple slopes for age by gender, where we have 0, 1. The simple slope for grip, still with the same typo. There we go. And it looks very much the same. And then, of course, Stata wins on the margins. You don't have to work nearly as hard in Stata because once you put in the values that you're plotting, then there are it understands that the interaction terms go into those predicted values. And so then I made two plots, one with age as the x-axis and then one with grip as the x-axis. All right, so any questions on the Stata code for that? Okay, then output time. So relative to our previous model, this is SAS output instead, the residual variance is about the same. It was 88 before. It's still 88. So that can't be good, right? If you add things and it stays the same, that means you still have the same amount of information left over that you don't know. F used to be 41 for the model and now it's down to 30. It's still significant, but it is lower. Any guesses as to why that might be? Why would our F for the model that used to be 41 go down to 30 after adding our two new interaction terms? Any guesses?
Does it have to do with the addition of two additional slopes?
It does. And the two slopes didn't change the residual variance much, which means they're probably not very good. So this F comes about by dividing by degrees of freedom. So it's, stop at word, it's this number, sums of squares for the model, divided by the degrees of freedom that gives me this mean square, and then this mean square divided by mean square error gives me F. So F is telling you per slope how good the model's doing. So previously with 5 slopes, F was 41 per slope. We added 2 garbage slopes. So we added to the numerator degrees of freedom, but we didn't really add to the model mean square. So the F is lower because it's an average contribution of more slopes and each is now doing less. And sure enough, R square is, I think it went up by like 0.01. So not a big change in that. We do have a huge sample though. How would I know if this R square is significantly higher than in the previous main effects only model?
Is that the test?
Yeah, the new test. So this F right here doesn't tell me that. This F right here tells me whether that R square is different than 0. To answer the question whether that R square is different than the previous R square, that's the new test. So I will skip down to that right here, the contrast. And survey says, nope. So yeah, the two new terms did not help the model. So the R-square may have gone up a tiny bit, but it's not a significant increase. All right, so this table here is something that Stata does not provide for you directly. These are effect sizes and semi-partial eta squares. Do you remember what those are? No?
Effect sizes?
They are effect sizes, but what do they mean? It's been a while. So these are the amount of the R-square for the model that each of these terms is responsible for. So this is kind of like the number of rooms that each child cleaned independently in my This Is Us example. So I have notes out here as to how to interpret these things. So I have age, for instance, is responsible for a semi-partial eta square of 0.002, and I have a note that says that that's okay, but it's conditional. What that means is that this effective age is not just the effective age. Given the interaction terms in the model, this is the effective age specifically in men. So the effect size that goes with it also has that conditionality. Likewise, the effective grip strength right here is specific to men. And so this effect size is conditional as well. Same with this effective gender, because gender interacts with age and grip. That is the gender difference specifically among people who are 85 and can squeeze 9 pounds. And so that's conditional as well. These are the two that we have to be careful with. The dementia group contrasts are not independent. And so their semi-partial eta squares cannot be used directly. We have to combine those. And so that's why I asked for this right here that does so. So in SAS, you can use contrast to not only lump two slopes together, but to get an effect size for that lump, so to speak. So the proper way to report semi-partial eta squared for a categorical variable that is represented by multiple slopes is from lumping those multiple slopes together. So dementia group as two separate slopes that create three different means is responsible for about 18% of the variance. So we only had an R-square of like 0.28, like 0.18 of it is responsible just for those two terms. And then the only terms that are unconditional are the interaction terms, because there's no higher order term that contains that same set of predictor variables. So this is something that Stata does not give you these semi-partial eta squares, which is why I only ask for them if they can be given by a test or a contrast statement to keep everything fair across the programs. So let's talk about what happened then. So intercept. We said last time that it was the predicted cognition for somebody who's 85, can squeeze 9 pounds, is a dude without dementia. Do I have to change anything about that sentence to make it work for this model? I don't. Because these two new interaction terms do not introduce any new conditionality. The variables are already in the model. So what the intercept is predicted to be is different relative to the previous model because it's a different prediction, but it's still the same reference point. Let's go through the list here. Is this marginal or conditional? The slope of age in this model. And what those words mean is this the slope of age for everybody? Or is this only the slope of age for certain people? Marginal is everybody.
It's only age for men, right?
It's only for men, exactly. So this is what's known as a simple slope. even though it is not simple, we should start a new thing and make it a complex slope. This is a complex slope because it is conditional. So you can't just look at it and say age matters or age doesn't matter because it's only for certain people. So in men, what would I conclude about the effective age?
Conditional or simple.
In men, so it's conditional. Let's go with significantly positive, non-significantly positive, significantly negative, or non-significantly negative.
Non-significantly negative.
Yeah, so the negative part comes from the sign. The non-significant part comes from the p-value. So in men, older people do a little worse on the test, but not significantly worse. Grip strength. Marginal or conditional?
Conditional again,
Mm-hmm.
and it is significantly positive.
Yeah. So in men, for every additional pound you can squeeze, your score goes up by 0.7. Yes, we're on a roll. How about this one? The main effect of gender. Marginal or conditional?
It's complex.
It is complex. But the answer choices in your homework don't have complex as an option.
A negative significant slope.
Yeah, it's negative and it's significant, and it is specific to what kind of person. So it's in two interaction terms, which means it's doubly conditional. Really complex. It's complexer than the other one. So this is the expected gender difference in people who are 85 and can squeeze 9 pounds. In those people, women are worse off. How about the dementia slopes? Marginal or conditional? Yeah, marginal. And we know that because they're the only ones. Yeah, they're not anywhere else in the model. There's no other term that conditions it. So these are the effects of dementia for everybody in this model. Dementia's bad for you, okay? That's my Mr. Mackey reference. Dementia's bad, okay? Last but not least, let's do this one. Skip ahead since we're about out of time. So I got a pattern here. The grip strength slope is positive in men. What is the interaction term doing to it? You got 4 choices. It's making it more positive, less positive, more negative, or less negative.
Less positive?
Ding. Ding, ding, ding. Yep. So is that making it stronger in women or weaker in women?
Is it that it's still making it? It's like it's making it stronger, but it's not making it as stronger. Like it's still increasing, but it's not like increasing more.
Yeah, it's still a positive slope in women. So it would be like 0.52-ish or something. But it's a weaker effect. So it's
less so in women? Is
Mhm.
that what you're...
Yep.
Okay.
I would say that the direction of the coefficient is that grip strength matters less in women.
Okay.
That's how I would put less positive into words that people would understand.
And that's because, Lisa, of the negative sign of the interaction term?
Mm-hmm. It's the combination of the positive sign for the main effect and then the negative sign for the interaction term.
And the main effect being grip in this
Yeah,
situation.
the way that we're going about it. I could flip it around and talk about the effect of gender as a function of grip, but we'll save that for next time.
Sure. Okay.
Yeah, so it's weaker in women. Is it still significant in women? Do I know that? It's not significant, or do I know that?
Not significant.
So here's the tricky part. This term right here is not significant. That is correct. This term is the gender difference in the grip slope. So it tells me that the grip strength slope is not significantly different in women, but there's nothing on this page directly that tells me what it is in women. I can do the math. It is roughly 0.52-ish in women. But that's where my friends say hello to my little friends. The estimate statements. Yeah, 0.52. Hey, I did that math all by myself. I didn't need cheat. All right. Yeah, so the estimate statements then do the linear combination of adding together what the grip strength slope is in men plus the interaction term for how it differs from women, and we get to the result, which is still significant. So grip strength does matter in each group. It looks like it matters non-significantly less for women. Yeah, I'm diverse. I have all kinds of pop culture references. Although I've never seen Scarface. I don't like violent movies, but I do know say hello to my little friends. Anyway. All right. Any questions before we call it a week? Not just a day, but a week. All right, then we'll pick this up next time on Tuesday. So have a great weekend. Let me know if you need anything, and take care. Thanks for coming. See y'all later.